All right. Okay, I guess we're recording. Cool. Took a while. All right, so we are on example 7. We are in the process of recognizing geometric series and then modifying that known series to create other series so that we don't have to, do as much work. Let's do example 7 very quickly here. The center is at 0. That's good. If we had changed the center, we'd have to come up with a new series. So 1 over 4 plus x doesn't look quite like the one we memorized. Remember, our basis for comparison is 1 over 1 minus x. And all the examples that have preceded this, we've really just had something different there. But now we have a 4 in place. So what can we do to make that 4 a 1? Do what with it? You could factor out a 1/4 from the entire thing. Yeah, it's essentially factoring out a 4 in the denominator, which makes that a 1 plus x fourths, like that. And then, of course, that's the same as having a 1/4 times the whole thing. All right, so that's the key there. And then plus x fourths, we're going to call that minus, because it has to be a minus. And then what then happens on the inside of the parentheses? A negative x fourths. So negative x fourths ends up being your r. R is equal to negative x fourths. All right, and now it is geometric. So let's go ahead and produce the one that we know so that we can modify it. We're building a series, all right? And now that we have it looking like this, we can kind of substitute in. So the one we memorized for 1 over 1 minus x, remember, is 1 plus x squared plus x cubed plus yada, 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 plus x to the n plus yada, yada, yada. Now, in terms of building this, what should we do first? Should we multiply everything through by a 4th first or substitute in first? Sub? Yeah, I would substitute in first. Is that what you said? Yeah, okay. So 1 over 1 minus, now we're subbing in a negative x fourths. And that's going to be 1 minus x over 4. When you square the negative, it's going to become positive. So now it's going to be x squared over, I'll just leave it as 4 squared, because the number is going to get kind of big. And the next one will be minus, now it's x cubed over 4 cubed plus dot, dot, dot. Remember, what you're trying to do is preserve the pattern. So sometimes if you simplify too much, like you called it 16 and 64, you might not see the pattern as a function of n in each term. So now it looks like it's going to be an alternating series, right? So you could say it's negative x to the n all over 4 to the n. That looks like the pattern. And then, of course, we can separate, like we want to do typically, we can separate the negative 1 to the n from the x to the n. So I'll go ahead and do that. Bless you. On the same line, negative 1 to the n times x to the n. All right, so I've got my power of x, I've got my alternator, and then I've got my powers of 4 that have the same power as n. All right, now I'm going to multiply through everything by a 4th. And when I multiply through by a 4th, I should end up with my final answer. So I'm just going to call this 1 over 4 plus x. And now I get 1/4 minus another 1/4 is going to be x over 4 squared plus x squared over 4 cubed minus x cubed over 4 to the 4th plus dot, 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 plus. And now I got negative 1 to the n, x to the n, all over 4 to the what? And plus 1. Good. Plus dot, dot, dot. Okay. Let's go ahead and figure out the interval and radius of convergence on this one, just because we haven't been doing that because they've been pretty much the same. All right. So if the center's at 0, to figure out the radius of convergence, remember, since it was written as a geometric series, then we know that the ratio, which is right here, the absolute value of that ratio has to be what? Less than 1, okay, by the geometric series test. So remember, for the geometric series test, do we need to test the endpoints? No. All right. So let me move this over where there's room. There we go. So, of course, now the absolute value doesn't really, or the negative takes care of the absolute value takes care of the negative. So we end up with just this is less than 1. And if I multiply both sides by 4, I get this is less than 4, which again is the same as x minus 0 is less than 4. So the radius is equal to what? 4, right? The radius is equal to 4. And because it's a geometric series, the interval of convergence is going to be slash domain of the series should be what? Negative 4 to 4. Good. Without the endpoints, correct? Without the endpoints. Now, we were going over the key that's posted online right now, the handwritten one on the notebook paper that's scanned in. I must have done that one super, super fast like 10 years ago when I made it. We found a couple of mistakes. I think there were like 4 mistakes on it. So use it as a guideline and not as a key, okay, if you get stuck. Here's the thing that we talked about, though, earlier. If I were to take the derivative of this power series or the integral of this power series, remember the radius of convergence doesn't change, but what might change? What do we need to check? The endpoints, yeah. And there was one on the worksheet towards the end where the original function converged only on the open interval, but then I had you take the integral of it. And if you test the endpoints, one of the endpoints or both endpoints end up working. Okay, so be careful like that. In this case, we're not taking the derivative or the integral of it. We know it's a geometric series, so it's going to converge on the open interval. Now, if we weren't sure, what could we do? If you weren't sure if it converged at the endpoints, what could we do? Plug it in. Yeah, now to plug it in, remember, you're going to need your sigma notation. So let's go ahead and extend that. This would be sigma from n equals some number, negative 1 to the n, x to the n, all over 4 to the n plus 1. And what I need to start at 0 or 1 to make sure my first term is a 1/4. 0. And we'll need to start at 0 because x to the 0 would be 1. All right, so if that is my condensed version now, let's go ahead and test the endpoints. Test the endpoints. You would say x equals negative 4, and then you plug it in, so you get sigma from n equals 0 to infinity of negative 1 to the n. Now, if I plug in a negative 4 to the n, that's going to be another negative 1 to the n times 4 to the n. Are you okay with that? That's the same as negative 4 to the n. Just saving a little bit of time. All over 4 to the n plus 1. Okay, so the question is always essentially what happens to the alternator? Does it stay or does it go, as the Clash asked musically? Well, negative 1 to the n times negative 1 to the n is negative 1 to the 2n. And is negative 1 to the 2n an alternator? No, it's not, okay? Negative 1 to the 2n is not an alternator because that's negative 1 squared to the nth power. So it ends up being 1. If you're not sure if it alternates without manipulating the exponents, what else could you do? Yeah, just plug in a couple of numbers, right? Plug in a 0, plug in a 1. And typically, if it alternates on the first 2 terms, it's going to alternate. But then you can always go to the third term and see if it alternates or not. So this one does not alternate, okay? So if it doesn't alternate and you simplify it, the alternator essentially goes away because it becomes 1. And what happens with your 4 to the n? It becomes 1 over 4 when you simplify, right? There's one more power of 4 in the bottom. And now this totally does what? This one diverges by nth term test, right? So we can't include the left endpoint. Let's try the right endpoint. If I do x equals positive 4, that's going to be sigma from n equals 0 to infinity of, now I plug it in here, and I just get negative 1 to the n times 4 to the n over 4 to the n plus 1. And there's nothing to worry about the alternator. The alternator is still there, but it turns into this. Now what happens to that? You get 1/4 minus a 4th, plus 1/4 minus a 4th, plus 1/4 minus a 4th. That also does what? That diverges. Again, by the nth term test. And so, as we concluded, before we even did all that extra work, it does not converge at either endpoint. And we know that because it was what type of series? Geometric series. So that's the benefit to recognizing a geometric series. You don't have to test the endpoints. Of course, unless you're taking the derivative or the integral of it. But for the series itself, it's a modified geometric. The endpoints don't work, and it saves you all of this time and effort. Okay? But you can always test them if you're not sure. Bless you. All right. Haben Sie any Fragen or preguntas over this? Or comments? Like, wow, that was fun. Green is a great color to use. Or anything? What? Use it more? Green. Yeah, it's spring. It's verdant, right? Okay. Is there like a pastel green that's suitable? No, that one's too light. Yeah, I'll use this green. Okay, classic green. All right, sometimes we cannot center our function at 0. In this case, we have to rewrite our function with the new center showing. Oh, find a power series that represents the center at 1, then find the interval of convergence. Okay, so if it's centered at 1, is it a Maclaurin series? No. What can we do? What can we always do? Yeah, we could do the Taylor's theorem, right? Let's do Taylor's theorem. Taylor's theorem. So remember, that work is involved, our center's at 1, but we're getting the numerators of the coefficients. All right, so why can't we center 1 over x at 0, make it a Maclaurin series? That'd be a lot more fun. Doesn't exist, right? So if f of x is 1 over x, f of 1 is 1. The next derivative, what's the derivative of 1 over x? Negative 1 over x squared, right? Which is negative x to the negative second. I think we've done this before. Does anyone remember what it was? Maybe not. Okay, let's just generate it. F prime of 1 then is going to be negative 1. The second derivative is in power form. It's 2x to the negative third. So f double prime of 1 is negative 6. I'm sorry, I'm taking the derivative. It's 2. I'm already on the next line in my head. The third derivative, that's negative 6x to the negative fourth. Yeah, so we're getting a factorial pattern emerge, right? So that ends up being negative 6. And it's also alternating. I'll go one more. Remember to go to Arabic with parentheses. The fourth derivative is positive 24x to the negative fifth. So the fourth derivative at the center is 24. Yeah, so this ends up being factorial. This is 2 factorial, 3 factorial, 4 factorial. This ends up being 1 factorial. That's negative. Sorry, these are negative. So it alternates. And this must be 0 factorial, which it is. So again, we're trying to see the pattern as a function of n, the derivative. All right, so here we go. The natural log, 1 over x, is equal or squiggles? Equal to, right? Because we're going to get a series, not a polynomial. So again, if we start like the tangent line, it's the y value of 1 plus the slope, which is negative 1 times x minus 1 to the first power. And then we pick up with the second derivative, so now it's plus 2 factorial all over 2 factorial times x minus 1 squared. And then it becomes minus 3 factorial all over 3 factorial times x minus 1 cubed. It said to do the first 4 non-zero terms, right? Now here's the deal. Sometimes they might ask you to take the derivative of something like this. Sometimes I might ask you for the integral. Realize if you take the derivative of the power series, you're going to be losing your first term. Okay? But we're not doing that in this case. So I'll stop right there, and then I'll just plus dot, 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 plus. And now I know I'm going to have an alternator, so it's negative 1 to the n or n plus 1. I'll come back and fix that here in a little bit. Do you want to try and get the pattern in Taylor's form? I don't think I will. Remember, that's always going to be this. That's the nth derivative at the center, all over n factorial, times x minus the center to the nth power. So you can go ahead and do that. That's Taylor's theorem. But this does simplify down to something a little bit nicer. 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed. Plus dot, dot, dot. I think we can simplify this now with the inherent pattern. Negative 1 to the n times x minus 1 to the nth power, right? So it looks like it simplifies down to. And now we just check. On the powers of x, that n has to be a what to get the first term to be a 1? A 0 or a 1? It's got to be a 0. When I plug that same 0 into n on the alternator, do I get the correct sign? I do. So remember, sometimes we might have to come back and adjust the alternator by putting an n plus 1 there. All right, and then for what it's worth, let's go ahead and say that that equals sigma. N equals 0. We already talked about that. Negative 1 to the n, x minus 1 to the n. So if you have space in your head, that is hard drive storage space, this one is probably not a bad one to memorize. It's not required. But it's nice. You can derive it pretty easily. All right. Is there a way to do that from a geometric series? The Maclaurin series, remember, is centered at 1. But if I can shift everything over 1 unit, including the original function, I might be able to scoot the polynomial over. In other words, if I were to write this as a centered at 1, could I write this as 1 minus x minus 1? That would scoot the whole function over 1. Yeah, you'd have to modify it. You'd have to have your x. So if you want it to be a minus 1, you'd have to turn around and do plus 1, right? X minus 1 plus 1, that's 0. And then if you switch that around, that's 1. And then it's plus x minus 1. But now to make that a minus, that would have to be 1 over 1 minus negative x minus 1. Like that. Next. Would that do it? Do I want to take the x? Actually, I want to leave it at like this. Yeah, because here's your x minus 1 now is you shifted it right 1 unit, which means that could show up in the center. And the fact that that's a negative there, that would actually work. You could actually let r equal negative x minus 1. And I think you could verify that pretty easily. If you looked at our geometric series then, if we plug that in for x, you would basically get 1, and then the next term when you plug it in for x is minus x minus 1. The next term when you square it, it's going to become positive. So you could actually do it that way. This would be a little bit faster, right? This would be a little bit faster. And then what would be also the advantage to this? If it asks you to find the interval of convergence, if you recognize it as a geometric series, you wouldn't have to test the endpoints. But let's go ahead, since we committed to this, let's go ahead and just finish the problem as if we didn't recognize it as a geometric series. How would we find the radius of convergence? What test do we typically use? The ratio test. Yeah, so let's find the radius of convergence. By the ratio test, I'll go ahead and write that down, the ratio test. We're going to take the limit as n goes to infinity of the absolute value. Do we need the alternator for the ratio test? No, it's a test for absolute convergence. So it's x minus 1 to the n plus first, all over x minus 1 to the n. And I'm going to work left to right here because I'm running out of room. That's going to be x minus 1. And remember, n is our variable for the limit, so we're treating x minus 1 as a constant. And what's the limit of a constant? Constant. So that just becomes the absolute value of x minus 1. Now, by the ratio test, that converges when it's less than 1. Yeah. And so if you recognize that as a geometric series, then remember you could just take your, whatever we called r up here, and take the absolute value of that and say it's less than 1. And of course the negative goes away, and then you wouldn't have to test the endpoints. So now we have it in that form that we like. It's x minus the center, and it's less than the radius. So the radius is what? It's 1 unit, right? Because it's x minus 1. 1 is our center, is less than 1. So if you want to draw a picture, it's kind of helpful. If the center is 1, remember they definitely converge at the center. But now I can drift 1 unit to the right and 1 unit to the left. And so a possible interval of convergence is from 0 to 2. But what about the endpoints? Do they work? Do they don't work? Okay. Well, if you recognize it as a geometric series, then it's game over, right? You know it's on the open interval from 0 to 2. So that would be the advantage if you stated that. But let's again say that we don't. It's not a bad thing to test out the endpoints. We're kind of reviewing. So let's go ahead and test the endpoints. We'll test the endpoints. So I got x equals 0 as one of them. So I already have my sigma notation there, so I'll just plug it in right there. So we get sigma n equals 0 to infinity of negative 1 to the n times negative 1 to the n. What is that going to be? That's just 1, right? So that's 1 plus 1 plus 1 plus 1. This one diverges by the nth term test. So we can't include that endpoint. And then at x equals 2, the other endpoint, we get sigma n equals 0 to infinity, negative 1 to the n. And now 2 minus 1 is 1. So we get 1 to the n. That one is going to be an alternator, right? Negative 1. It starts off at 1. 1 minus 1 plus 1 minus 1. This one also diverges, also by the nth term test, a very good test to use. And so, now if it asks you for the interval of convergence slash the domain is the open interval from 0 to 2. The open interval from 0 to 2. So again, the whole point of this section is if you recognize it as a geometric series, and you don't have many like this where you change the center, okay? The ones that you might have to do are probably limited to example 7. But most of them are like example 6, where it's a real easy modification. Unless you're taking the derivative of the integral, you do not have to check the endpoints, all right? Now, before we move on, let's actually do something here. Let's go ahead and sketch the graph of 1 over x in y1. 1 over x. Okay, sweet. Now, there is a way, and Skylar did this the other day, which kind of gave me the idea to do it this way. Instead of typing in term after term after term after term, if you wanted to sketch any polynomial, because of course we can't sketch infinitely many terms, but if I wanted to start typing in some of these terms to see if it is in fact becoming the graph of 1 over x on the interval from 0 to 2, which of course we know it couldn't be at 0 because there's a vertical asymptote, you can actually use the rule of sequence right here, or this version here. So I'm going to go ahead and type this into y2. You type in your sigma. Okay, you have to use a different variable though. You can't use x here. You can use n, a, b, c, whatever. I used a because it's real easy, alpha a. And we're going to start at 0. And I'm going to go ahead and try and do this. Click to the right. I'm not going to do 19. Let's start with 5. And if I type in my rule of sequence now, let me get rid of that. It is parentheses -1 to the 8th power. And then to the side, parentheses x. This is where x comes in, x minus 1 to the 8th power. Okay. And again, as long as this a and add a match this a, you can call it any variable. So that's going to give me a 5th degree polynomial, okay, which could be an approximation for 1 over x. Let's go ahead and set our window. If it's converging from 0 to 2, let's go from -1 to 3. Okay, so we can kind of see where it diverges outside of that. All right, so here's the graph of 1 over x. And there you go. So notice at 1, this 5th degree polynomial is exactly the same. And the red one that came in there is that 5th degree polynomial. Now let's go ahead and amp it up to 20. Let's see if it does 20 terms. It might take a while. So this will be a 20th degree polynomial. And that's exactly the same now at 1. And now you notice that it's starting to look like the blue graph on a larger radius. Well, the idea of the series, remember, is that if you were to use infinitely many terms, the red graph would be a perfect representation of the blue graph, but only on the open interval between 0 and 1, okay? At 1, it's going to be a different value, and of course at 0, where the blue graph doesn't exist, it's nothing, okay? So that's what we call the interval of convergence. It's on the open interval from 0 to 2, and for infinitely many terms, which is physically impossible, the red graph becomes exactly the perfect blue graph, right? There you go. So there's a visual of the interval of convergence. Comments or questions so far? Like, wow, I'm really digging the green color still. All right. By the way, on the day of the AP exam, remember, don't abbreviate anything, okay? You can do MVT, IVT, EVT, max, min. That's about where it ends, right? You want to write everything else out. All right. You want to do number 9? It says it's a bit of a booger. We are using green. Boogers are green usually, so let's try it. Let's try it. Find a power series for this centered at 1. Okay? And then find the interval of convergence. All right, so based upon our insight from the previous problem, let's try and generate it without having to use Taylor's theorem. Derivative, 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 derivative. But if it's centered at 1, our goal is to get it as 1 over 1 minus, there's got to be an x minus 1 in there, because that'll shift everything over. Okay, so here we go. I'm going to take the 15 out, because he's really not going to come into play. right? He's just a constant multiple. So 15, you go out. And then I got a 1 over 2x minus 1. Okay, now what? Well, let's flip it around, shall we? Let's actually factor out a negative 15 and make that 1 over 1 minus 2x. Is that okay? That's okay. All right, so now that kind of makes it look good. I got a 1 over a 1 minus. If this were a Maclaurin series, I'd be good, right? I would just call the ratio 2x. But it's not a Maclaurin series. I want to center it at 1. So if I can write this, shift it over 1 unit, I've got it. So we're going to do the same little trick that we did in the previous problem. I'm going to put minus 2, and then inside, I'm going to add a clever form of 0. Clancy mentioned this earlier, right? I'm going to call that x minus 1, and then plus 1 on the inside. What's minus 1 plus 1? 0, right? Now, what I'll do, since I want to keep that there, let's go ahead and distribute that negative 2. So I got negative 15 over 1 minus, if I distribute, I get a negative 2, and then minus the 2 times x minus 1. So this minus 2 came from distributing. The other minus 2 is the one that's in front. Okay. So it's starting to shape up. A little bit more moving stuff around. And that becomes 1 minus 2. That's now negative 1 minus 2 times x minus 1. And now I think if I do one more thing, I'll have it. That has to be a positive 1. So I'm going to now factor out the negative from both terms in the bottom. And that makes it back to another positive 15 over 1 plus 2 times x minus 1. And now seriously, folks, last step. Seriously. I need to make that a 1 minus again. So now that's 1 minus bracket negative 2x minus 1. Might there be an easier way to do that? Sure. This is just the way I saw it. So now I have it as 1 over 1 minus, and I've got my x minus 1 there, which shifts the series over 1 unit. So that's a little bit of algebraic manipulating. But now, because it's in that form, this is a geometric series. And so I don't have to test the endpoints. Let's go ahead and build it. I start with 1 over 1 minus x, which is 1 plus x squared plus x cubed plus yada, 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 plus x to the n plus yada, yada, yada. Don't forget the ellipsis points at the end. And now I will build it by replacing our r is negative 2x minus 1. So if I replace that for x, I get 1 over 1 minus negative 2 times x minus 1. It becomes 1 minus 2 times x minus 1. When I square it, it becomes plus 2 squared x minus 1 squared. The next one's going to be a minus 2 cubed times x minus 1 cubed plus dot, 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 plus. Now, then I'll just go ahead and do the full replacement here. It's negative 2 to the nth times x minus 1 to the nth plus dot, dot, dot. So all I did there is I separated the number. I still haven't separated the alternator from the number. You see that? I just did negative 2 to the n, x minus 1 to the n. But on the next line, I'll separate it. So the last thing I need to do is do what? Multiply everything through by 15. Okay, so now I get 15 over, and I can go straight to my 2x minus 1. 15 over 2x minus 1 is now equal to 15 minus, I'm just going to call it 15 times 2 times x minus 1 plus 15 times 2 squared times x minus 1 minus 15 times 2 cubed times x minus 1 cubed. And now I'll simplify the nth term, plus dot, dot, dot. I'm going to have my negative 1 to the n times the 15 times the 2 to the n. Okay, here's the splitting up of the negative 1 and the 2. And then the variable part, x minus 1 to the n, and then plus another dot, dot, dot. So I snuck it in there. Wow. And now let's do one last thing. Let's go ahead and write this in sigma notation. From n equals something to infinity of this wonderful looking rule of sequence. Negative 1 to the n times 15 times 2 to the n times x minus 1 to the n. Let's do two things. I didn't really check over here, but what n would I have to start with to make my first term just a 15? N would have to be a 0, right? So check the alternator. Negative 1 to the 0 is positive, so that keeps it positive. So this works, and now I know I have to start at 0. So if we wanted to, we could do the same thing. We could sketch the graph of 15 over 2x minus 1 and y1, and then we can generate more and more terms of this right here, and it'll get closer and closer and closer to the actual function on what interval. What is the interval of convergence? The radius of convergence is, well, we haven't done that yet. Let's do that. This is our r, okay? So it's the absolute value of negative 2 times x minus 1, which I know equals just 2 times x minus 1, which has to be less than 1 by the geometric series test, not the ratio test. And so if I divide through by 2, I get x minus the center is less than a half. So the radius of convergence is what? 1/2. And the interval is what? Remember, your center's at 1. So if you're at 1, you go left a half to what? 1/2. And you go right a half to 3/2. And I can put parentheses around both of them. Why? It's a geometric series. Good. All right. If I didn't identify it as a geometric series, I would have to then test the endpoints. And you'll see that neither one of them works. But again, if I were to then take the derivative or the integral of this, which is what we're doing in subsequent examples here, then I would have to retest the endpoints because one of them could now work all of a sudden. All right, sweet. So that one's a bit of a booger. You're not going to have to do one like that. But as much algebraic manipulation as we did, I think it's probably still a little faster. Maybe not. I don't know. Maybe if you did Taylor's theorem, you would have had it sooner. Okay, moving on here. We can now integrate or differentiate a power series to obtain a new series. But remember, when we do this, the radius is the same, but the interval may change. We have to retest the endpoints. Okay, we've been talking about that. All right, so here we go. Find a power series that represents 1 over 1 minus x, centered at 0. And now it says, hint, what is the derivative of 1 over 1 minus x? So if this were a free response question, it would probably not give you a hint, but it might be on part A, write the series for 1 over 1 minus x. Part B might say take the derivative of that to create a series for this. All right? So this is not a geometric series, is it? It doesn't look like it because it's not 1 minus the quantity x squared. It's the quantity 1 minus x squared. So how can we use the power series to generate it? Well, what is the derivative of 1 over 1 minus x? Well, let's see. That's going to be 1 minus x to the negative first. That's going to be negative 1 times 1 minus x to the negative second times the chain rule, another negative 1, which makes it positive 1 over 1 minus x squared. Is that the series we're trying to come up with? Yes. So here's our plan of attack now. Instead of starting from scratch with Taylor's theorem, I'm going to write the Taylor series for 1 over 1 minus x, for the Maclaurin series, either one, and then I'm going to take its derivative, right? Okay, so here we go. Let's break this down into like potential free response stuff. Part A, write down the Taylor series for 1 over 1 minus x, or it might say the Maclaurin series. If it ever says Taylor series, it'll always tell you what the center is. So again, that's the one you memorize, 1 plus x squared plus x cubed. It says the first 4 non-zero terms, or it doesn't say that here, but it will. Okay, it should. So can I just write those 4 terms? If I'm going to be taking the derivative, the 1's going to go away. So I'm just going to be careful and write one more extra term. You can always go past the first 4 non-zero, but they have to be correct, which I'm pretty confident these are correct. Plus dot, dot, dot. All right, so now the derivative of both sides, the derivative with respect to x, this might be part B, of 1 over 1 minus x. Come on, there we go. Is, and then we would show the work that we did right here. We would show that work, and we end up with 1 over 1 minus x squared. And then it would say, and then use that result to write a power series for that. So you could say, okay, then that is equal to the derivative of what we have above. I'm not going to show the derivative of the right side of that, like d dx parentheses. I'm just going to go ahead and take the derivative term by term, okay? So the derivative of the first term, 1, is 0. Good. And the next term, x, goes to 1. X squared goes to 2x, and then 3x squared, and then plus 4x cubed, plus dot, 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 plus, what's the nth term going to be? N times x to the n minus first power, plus dot, dot, dot. Okay. Now it's to find the radius or interval of convergence. The radius of convergence is what? When you take the integral or the derivative of a function to get a new function, a new series, the radius will never change. It's the same as the radius of what you started with. The interval of convergence might change, though, because the endpoints might. So what was the radius for 1 over 1 minus x? It was 1, right? It was centered at 0, and it was from negative 1 to 1. So the radius is, I'm going to say 1. I almost wrote still 1. Like, it's still 1. I don't want to do that because I never said what it was. But the radius is 1. Okay? So if you draw your little number line, it was centered at 0, and you could do this kind of for every problem. You know it's going to converge now on the open interval from negative 1 to 1. The endpoints never worked for 1 over 1 minus x, but I took the derivative, which means now I have to retest the endpoints, okay? So let's come over here, and we'll write our sigma notation. That equals n equals something to infinity of n times x to the n minus 1. In order to get my first term to be a 1, this x must start with what n? 1 or 0? 1. Okay? Must start with a 1. So you always check that. And there's no alternator to check the sign of. Okay, so let's test the endpoints. We're going to test the endpoints. We'll do negative 1 first. We test x equals negative 1, and you plug it in. So it's series sigma from n equals 1 to infinity, n times negative 1 to the n minus 1. Is negative 1 to the n minus 1 an alternator? It is. Yeah, it's pretty much the same as n plus 1. So it is an alternating series. So remember, to be an alternating series, what's left without the alternator has to decrease to 0. Those are the two things. The terms have to be decreasing and approaching 0. Does n decrease and approach 0? No. So guess what? This one does what? Diverges by what? Nth term test or alternating series test? Nth term test. Yeah. Be careful. Remember, the alternating series test is not a test for divergence. It's a one-way test for convergence. But if it fails, it's going to fail because of the nth term test more likely than not. Okay? All right, so I can't include the left endpoint. Let's test the next endpoint, x equals positive 1. You're getting sigma from n equals 1 to infinity. Now you're plugging it in, and you get n times 1 to the n minus 1. What happens with that? 1 to any power, truly 1 to any power is 1, so n is going to be 1 plus 2 plus 3. This also diverges by what? By the nth term test. So it turns out that we weren't able to include an endpoint here. So the interval of convergence, write it out, the interval of convergence / domain of the series, if you want, is still going to be negative 1 to 1, non-inclusive. Last Friday, when a lot of y'all were sick, we worked the 6th question on last year's AP exam. It's typically the 6th and final pre-response question on the AP exam is the sequence and series. Or it could be a polynomial. It could be Taylor polynomial as well. They're very closely related. And then you'll have kind of like a sprinkling of some of these throughout the actual test. All right, so far so good so far? You know what? We're not going to finish today, which is what? It's okay. It's okay. If you are understanding this as we go, we're not going to have to review this in the next couple of weeks, 3 weeks, which is good. It'll be fresh in your head. You can go in. All right, let's see if we can squeeze one more in before we take a stand. Find a power series that represents the natural log of 1 minus x centered at 0. Now, again, you can always go straight to Taylor's theorem and produce the coefficients of the numerator's coefficients. But again, this could be an AP question, and they might lead you to what you need to do. It says, hint, what is the antiderivative of 1 over 1 minus x? So let's go ahead and ask it in that format. Let me say part A. It might say, what is the series for 1 over 1 minus x? Good thing we have it memorized. It's 1 plus x squared plus x cubed plus yada, 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 x to the n plus yada, yada, yada. Assume it says to write the first 4 non-zero terms and the nth term. All right, so part B. It might ask you, what is the integral of 1 over 1 minus x? All right, so let's work on that. This goes all the way back to 4.4. If you put that in parentheses and put it to the first power, now it is a pattern recognition. We have an inside function of 1 minus x. What is the derivative of 1 minus x? Negative 1. Do we have a negative 1 on the top? No, but we're only off by a constant multiple. No problem. So if I have an unwanted negative 1, all I have to do in my answer is put its reciprocal as a correction, which is still negative 1. If we had generated an unwanted 5, remember, we would have a 1/5 in our answer. And now we're done with the inside function, and now we move on to the rule of integration. Whenever your inside function is in the bottom to the first power, what is the rule of integration? Natural log. So it's the natural log of the absolute value of 1 minus x plus c. Yep, plus c. All right, so now it might say to use your result to find a power series that represents this centered at 0. Centered at 0, okay? So let's see. If I could take the integral of the power series, it should represent that right there. Natural log of 1 minus x. Okay, I could do that. So let's go ahead and do that. Same part. We'll call it part B as well. The integral of 1 over 1 minus x dx is going to equal what? Well, let's go through and integrate each term. Now, what should we do first? Yeah, let's put c first. Instead of plus c at the end, which is okay to have it at the end, we're not quite used to doing this, but as long as you remember to put it somewhere, the beginning is now the best place to put it. So c plus, and then what's the antiderivative of 1? X, and the antiderivative of x is 1/2 x squared plus, the next term is 1/3 x cubed, and I'll do one more since I have it, 1/4 x to the 4th plus, dot, 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 plus, and then it's x to the n plus 1 all over n plus 1 plus dot, dot, dot. So you can manipulate the nth term the same way. Now, this we just said should equal the natural log of 1 minus x. Now, because we're centering it at 0, this is where the absolute values can kind of be dropped. If we're centering this at 0, our x is positive. Unless my radius is going to extend somewhere that's going to make that negative, it should work. That's equal to, not that though, actually it's equal to what? I'm forgetting the negative in front, right? Yeah, negative plus c. All right, so I'm trying to come up with the power series that represents that. So now what can I do? I have essentially an equation. This equals that. And what I'm trying to solve for is this. So what can I do to solve for that? What happens with my plus c's? They actually cancel from both sides, whatever the initial condition is. Now, if you want an initial condition, you could actually plug it in. You could plug in the center, right? They're always going to be the same at the center. So if you needed it, plug in a 0 for x. What do you get? Natural log of 1 is 0. So you can use 0, 0 as an initial value, but you're going to see that it ends up being 0 anyway. Okay, so now what do I need to do since the c's cancel? Divide by -1. So here we go. The natural log of 1 minus x. And I'm going to drop the absolute values here because when I come back for the interval convergence, we'll see if there's a value that actually makes it negative. It's going to be the negative of all that. So negative x minus, I'll put the x's in the top. We typically do that just to clean it up. So minus x squared over 2 minus x cubed over 3 minus x to the fourth over 4 plus dot, 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 plus. Can I put plus even though they're all minus? Yeah, that's fine. Negative x to the n plus 1 over n plus 1 plus dot, dot, dot. Okay, so that should work. And now I just need to check the interval of convergence. So let's go ahead and condense this down into sigma notation. We're going to start at some n. We're going to go to infinity.
Good morning, Unicorn. Happy Monday. Hope everyone had a fun day.
We had a great day. We need to start at 0. Okay, we're going to start at 0.
On the text slide, I pledge allegiance to the text, one state under God, one and indivisible. Please remain standing for the moment of silence.
Thank you.
All right. While she's talking, just remember, since we modified a geometric series, the radius was 1. The radius is still 1.
Also, seniors, just a reminder,
the radius is still 1.
Down or any graduation announcements, you will be able to pick them up tomorrow during all lunches.
The interval of convergence, though, could include an endpoint now because we integrated. So we have to use the nth term rule of sequence to test the endpoint. So I did that over here. So at x equals -1, we end up with this.
Stop by the library this week to check on your account.
That negative can actually come out front. Okay, because it's a negative coefficient. What do you know about this now? Yes, it converges. It's an alternating series. So you could say since what's left, 1 over n plus 1, decreases to 0. Okay? It decreases to 0. That's the two things you need to say. This thing converges by the alternating series test. So we can now include the left endpoint, which we couldn't before. And if we test x equals +1, we get, I'm going to pull the negative out front again, sigma n equals 0 to infinity. You get 1 to the n plus 1, all over n plus 1. Well, what's 1 to the n plus 1? It's just 1. So we end up with just 1 over n plus 1, which is what? Con or divergent? It's convergent. No? This is divergent. It's a divergent. It's 1 off a p series, right? It's 1 off a p series. If it were just 1 over n, that is your divergent harmonic series. If you needed to do a real test, would the direct comparison work? If 1 over n diverges, you would have to show that this one is bigger. Is 1 over n plus 1 bigger than 1 over n? No, so that wouldn't work. But you know the plus 1 has no effect on it, right? So this one still diverges. You would have to use a limit comparison test. So I'm just going to say it's a divergent p series. Okay? You're not going to have to go full out and do the test here. If they did that, they would structure it as a separate question. So it essentially diverges because of the p series comparison. Okay? P series 1 over n. All right? So we can't include the right endpoint. So here we go, the final answer. The interval of convergence / domain of the power series, same thing, is -1 to 1, but can include 1 and can include the left endpoint now. That's pretty cool. That's pretty cool. We picked up one more point along the way. All right? So we saw one where nothing really changed. The endpoints weren't included. When we differentiated, here we integrated and we were able to include one endpoint. Sometimes you might be able to include both of them. The thing to remember, though, is when you take the derivative or integrate a known series, whatever it is, geometric or other, the radius stays the same, and you just retest the what? Endpoints. Okay, sweet. I think we're going to stop right there. Tomorrow, we will definitely finish, and this is good. You could think of this as like our first day of review. It's a question that's similar to the last question on the 2008 Aloha exam, as I call it. It's the Form B, which the Pacific Islanders get. Because of the time difference, they get a different test, right? So it was the last question on the test, and I just changed a couple of the numbers, but you will, if you were here on Friday, it's going to feel kind of similar, right? We'll do that, and then we do this last little example here. The only series that we can find exact sums of are geometric series, telescoping series, and now we're going to add to that a known power series evaluated at a point. Okay, and that's what example 13 is. So, any comments or questions before we end today? National Picnic Day. Some people said my shirt reminded them of a picnic cloth, and I'm like, cool. I guess I'll get crumbs on myself at lunch and celebrate. A couple of ants. Yeah. All right. Any other comments, though, before we stop? They're going to be listening to this video in China. You want to tell them anything? Hi, China.